Thanks. Thank you for the introduction. Thank you, Clara and Florian, for organizing this workshop. So I will tell you today about some work that we've been doing on quantum neuromorphic computing with superconducting circuits. So most of the results that I will present today have been done by Baptiste Carle and Julien Dudas. And I hope you have already met Briac and Loris. If you haven't, they're here and you can talk to them in front of their posters. Okay. So when we talk about quantum neuromorphic computing, I think of it as an analog approach to quantum neural networks. And in that sense, there are kind of two groups of networks. There is quantum reservoir computing and parameterized Hamiltonian evolution. And I think it's funny to notice how there is a historical parallel in a way between classical reservoir computing that was first proposed as a solution to the training problem of recurrent neural networks, where you have this recurrent loop that when you need to calculate the derivative of the loss function with respect to this weight, you get this large product of the same primitives. And then if this derivative is smaller than 1, you get the problem of vanishing gradient. So you're kind of stuck and you can't train your network. So the solution was proposed by Herbert Jaeger in a simple way. He just said, well, okay, let's not train the weight and let's add some dynamics to the system. And then people realized that these dynamics, you didn't need to simulate it. You could use physical systems and get it for free. So there was a large number of different implementations. Here I've just shown two, one with optical systems and one from Julie's group with spintronic nano-oscillators. But there is a lot of other ones. And then, people realized also that reservoir computing is a bit limited because, in essence, it's a shallow neural network. You only are training a single layer. So they moved on towards training systems. But with quantum systems, quantum neural networks, everything is happening a bit later. We kind of run into the same problem, same but different. So the first approach to quantum neural networks were these parameterized quantum circuits, where you have a circuit-based quantum computer. So you have some qubits here, which are represented by lines, and then you're applying some gates on these qubits. And you can actually parameterize the rotation angles of these gates and treat them as trainable parameters. And use the same toolbox as you use for artificial neural networks. So in the beginning, people were really excited about this because the size of the neural network that you can have, the number of neurons, is kind of proportional to the dimension of the Hilbert space, which is very big. It's exponential in the physical size of the system. And the first experimental implementations actually confirmed this, that with a very small number of qubits, you could have an exponential number of neurons. So this looked really cool until people tried scaling them even a little bit more up by making them a little bit deeper, so applying more layers of gates. And then they run into this problem called barren plateaus, which actually comes from the same fact that we were initially excited about. So this very large Hilbert space gives you a problem that, some areas of that big Hilbert space are flat. They're unpopulated, so the gradients vanish, they go to 0. And these are called barren plateaus, these flat areas. And then, the community found the same solution as the one for recurrent neural networks, which was, let's not train the system. Let's use quantum reservoir computing. Okay, but we already said that quantum reservoir computing is not super interesting for any deployment, let's say. So why do we do this? Like, what can quantum systems bring to reservoir computing? So already in this first paper, where quantum reservoir computing was proposed by Fuji and Nakaima, they noticed that when you're using a quantum system to implement reservoir, you actually get a lot of hidden neurons that participate to transformation of input data that you are not measuring, because you're only measuring a subset of states. And they could show that to solve some benchmark tasks, you needed to measure a smaller number of neurons than with classical systems. So these actually seem to participate to data transformation. And then the another advantage is that, well, quantum reservoir being actually a quantum analog system, it can naturally couple in the quantum domain to input quantum data. So you can learn to classify or recognize some states without having a measurement here in between or a classical sensor. And they show that they could actually learn a lot of different properties of a state, such as the quantity of entanglement or entropy. Okay, so this is kind of what has been driving us as well to use quantum reservoir as a probe for quantum physics, to see what can we learn about how quantum systems process information. And we wanted to do this experimentally. And this is why we choose to do it with the bosonic mode, because it's a hardware efficient approach to the problem. As in a single mode, you can get a much larger number of quantum states. So what we do is we treat different levels in a mode as, so different Fock states as neurons, and their outputs are occupation probabilities. And we can implement this using a superconducting circuit. So the circuit we use is shown here. The green line here is a superconducting strip, which hosts different modes of the electromagnetic field, and we use the lowest frequency one, the fundamental one, so it's called lambda over 2. And you see this mode here, it has an inductance that is given by the length of the strip, and the capacitance that is given by the capacitive coupling to the ground plane. So this is an oscillator, right? And if you put it into a dilution refrigerator, then you can calm down the excitations of the environment, and you can actually resolve the energy levels in this circuit, because these are typically in 5 to 10 gigahertz range, and this is about 100 times larger than the temperature fluctuations that you have in the dilution refrigerator. Okay, so this is going to be our reservoir, this mode. And then we capacitively couple a qubit to it. So this is a Transmon qubit. It's the simplest qubit that we have. It's just a Josephson junction in parallel with a capacitor. But we don't use qubit for processing here. We use it only as an ancilla. So this is really a workhorse of superconducting circuits. It's dispersive coupling. So it's this term here. And you see, it actually makes the frequency of the qubit depend on the number of photons in the cavity. So this is something that we can see here. This measurement is called a two-tone spectroscopy. Two tones because we apply simultaneously a tone on the cavity and on the qubit. So y-axis is the cavity, and you see larger the cavity drive, more photons we have in the cavity, okay? And then here we see different qubit resonances that correspond to different numbers of photons in the mode. So when I go to larger cavity drives, I have larger probability to have 4 photons. and this is why I see this resonance appear. Now, the way this measurement works is that we're going to try to excite a qubit at a certain frequency. So we're going to apply a selective pi pulse at the frequency that is dressed by n photons in the cavity. And if we find the qubit excited after that, then we can conclude that indeed there was, or there were, n photons in the cavity. And then we repeat these binary questions. And the way the whole sequence works is that we encode the input data into the drive of the cavity. So if we have some temporal task, then we send pulses one by one whose amplitudes are proportional to the data that we're encoding. And then we perform a readout through the qubit. Now, this is what these occupation probabilities look like. So here is the probability of different photon numbers, 0 to 4, as a function of the input amplitude. So first thing that you can see is that these are nonlinear functions. So this is exactly what we need to implement reservoir computing. And also they're all different from each other. So this is a bit unusual, but why not? It can work. Now, we can only measure photons with sufficiently good signal-to-noise ratio up to 4, which gives us a total of 5 neurons. That's not much. So what we can do to improve this is to sample at different moments during this pulse that encodes the last data point. So at 50 nanosecond intervals, we are going to ask the question how many photons they are. So this gives us a total of 20 neurons. Now, the benchmark task that we address, it's our favorite task in the group. It's a sine and square waveform classification. There is a couple of reasons why we like it. First, it's a one-dimensional task, so it's really convenient. Experimentally, you only need to send one point at a given moment. So you send these points that are equal to -1 or +1 for a square, and that take different values for a sine. And at each time step, you ask the network, does it belong to a sine or to a square? So this task is actually not easy to solve. You see that it's nonlinear. You can't just draw a line to separate the two classes. And it also requires memory from the network, like to remember to distinguish these points that can belong either to sine or to a square. You need to remember where you're coming from. And these are experimental results. You can tell by how noisy they are. So here with 20 neurons, we reach a really high accuracy of 99.7%. But interestingly, if we choose the most informative out of these 20 neurons, so we just pick the ones that work the best, 8 are sufficient to reach almost the same accuracy of 98.6%. So now to actually learn something from these results, we need to compare this to something else. So what we do is we compare accuracy that we can achieve with different number of neurons that we measure in different types of reservoirs. So the blue one here is a previous work that we have done here by Julien of 2 bosonic modes coupled, and is the same type of measurement. We measure the occupation probabilities on the state that we prepare. And you see that already with 9 neurons here, we reach 100% accuracy. Now, we can compare that, so the red point here is our experiment, okay? We can compare this to a classical reservoir with just a rectified linear unit function. And you see that we need much more neurons, more than 25, to reach the same accuracy. And now to see if all this advantage is coming from the fact that the system is quantum, we have also compared it to a classical dynamical reservoir. So for this, we have taken this spin torque nano oscillator that we also have experiments with them in our group led by Julie. And you see that dynamics already helps a lot. So definitely not all the advantages coming from the fact that the system is quantum. And then we also induce strong dephasing rates to our system, and we obtain this orange curve. So everything in between orange and blue seems to really be coming from quantum coherences in the system. Now, we're quite happy about this, especially the fact that we reached these high accuracies despite the measurement imperfections. So something that I kind of didn't tell you immediately is that we don't really have this perfect dispersive Hamiltonian. So this dispersive coupling that we get from the nonlinearity of the Josephson junction comes also with a side effect, which is a higher order nonlinearity term coming from the Josephson junction. So you see that these resonances kind of bend a bit to the left. And this is because the nonlinearity of Josephson junction is really strong. So already at a single photon level, we have this Kerr effect. So it's in particular this self-Kerr that annoys us, which makes the frequency of the mode depend on the number of photons in the mode. And, well, this has good and bad sides. The bad side is that our readout is less efficient because we're always reading at the same fixed frequency. So we fit this by a straight line because we don't want to add any inductive bias. So we don't get the correct answer sometimes for this question. But we do get more nonlinearity. So to test this trade-off, does the Kerr nonlinearity actually help us or make things worse? We performed these simulations. So we needed to do simulations because once you have your sample, the nonlinearity is determined by the Josephson junction that you have and the capacitive coupling to it that you have. So you can't really tune it experimentally. But what we see okay, let me guide you through this plot. So what you see here is the error. So we want it to be purple. It's good when it's purple, when it's small. As a function of the Kerr effect on the x-axis and as a function of detuning. So this is to kind of compensate for the Kerr effect. And you see that the best ones we get up here. So here the encoding range that we use for our input data is the largest. So okay, this makes sense. More you split the input points the most, the signal to noise ratio that you get is the best. But also what you see is that the best performances are at the bottom left. So bottom left, the Kerr effect is large. So this is quite cool for us. It means that we can use this Kerr nonlinearity that anyways we can't really avoid, despite the fact that it reduces the measurement efficiencies. So, okay, this was about reservoir computing. Reservoir computing, it's a nice tool to probe the dynamics of your system, to gain some insights. So we learned that quantum coherences do matter for learning, even on input classical tasks, and that Kerr nonlinearity added to that measurement nonlinearity that we have actually improves performance. But, okay, so people already learned in classical neuromorphic computing that you can't go very far with reservoir computing. And in quantum reservoir computing, it gets even worse because measurements are so expensive. So, and in reservoir computing, you need to measure a lot of variables on your system because all the learning is happening afterwards. So you have to have something to learn on. So we would really like to train parameters in the system, so this parametrized Hamiltonian evolution that I mentioned in the beginning, to concentrate the information on the smallest number of degrees of freedom to measure. But this brings us to a million-dollar question that we've been talking about a lot here, which is how to train a physical neural network. So it's already hard with classical systems, and it doesn't get any simpler with quantum ones. In some cases, as proposed by Logan a couple of years ago, you can use backpropagation in the case when you have a good model of your system and what is very important for quantum case, you can efficiently simulate it. But the problem is that there is not many quantum cases when you can do this. I will tell you in what follows about a particular case, which is a system with linear dynamics, where nonlinearity comes from the measurement. So we can simulate and differentiate this model. But this can't be generalized to all systems. And then I will not have time to tell you today about, but once again, you can go talk to Loris and Briac in front of their posters about other methods that we are trying to adapt to our experimental system. Now, how can we use backpropagation? Well, first we need something to train, right? So we need to introduce some parameters, and we do this by using these parametric couplers. So in superconducting circuits, there is a whole zoo of different parametric couplers based on Josephson junctions that you can use. And actually, some of them implement pure three-wave mixing. So there is no this annoying Kerr term. So it's called snail, one of the most well-known elements that does this. And once we have this three-wave mixing term, you see we can pump it at different frequencies. So if we pump it at the difference of the frequency of the two modes, then we get this coherent conversion term. If we pump it at the sum, we get a parametric down conversion or two-mode squeezing. And then we can train the amplitudes of these drives. We can also train the detunings of the resonant drives that we apply on our mode. So all the parameters that they put in red here is what we're training. So we do have an analytic solution for the gradients of the loss function with respect to these parameters. So we can use a gradient descent. And also we can obtain the outputs of the networks through Gaussian-Boson sampling. Okay, so this is really the cool thing with the superconducting circuits, the fact that we have these photon counters that go up to higher numbers of photons, and this is something that we can do quite easily. And now, what do we obtain? We address the same sine and square classification task. And you see that now we are measuring only a single probability, whereas before we were measuring 9 or 8, depending on the implementation. So with two modes, 9. And in about 100 epochs, we reach 100% accuracy. But it actually gets even better than this. As we're only measuring the lowest probability, so here we're measuring the probability to have 0 photons, so this is the state that has the highest occupation, we can actually estimate this probability with a smaller number of measurement shots. So here, what I'm showing is the accuracy as a function of the number of measurement shots for reservoir computing. So you see that we needed 10 to the power of 8 shots, that's a lot, to reach the same accuracy as with the exact probabilities for these higher states. Whereas here, even taking the training into account, so 100 epochs times 10 to the power of 3 shots, we still have a smaller measurement budget in total. Okay, so we were quite encouraged by this, and we decided to try some harder tasks. So we tried learning these spirals, and it didn't work at all. So here we were still encoding in the resonant amplitude of the resonant drive. So we thought, okay, maybe we don't have enough nonlinearity. We can try to encode in the angle of one of the pumps, and it worked super well. So our first explanation why it works was that angle gives us more nonlinearity. So we tried encoding in different parameters. And here you see accuracy is when we encode in the amplitude of resonant drives, of two-mode squeezing, or in phases of amplitudes and two-mode squeezing, and in the amplitude of the coherent coupling. And here we see something that we didn't really expect in the beginning, which is that it's not really phase that works well, it's the two-mode squeezing. doesn't matter if it's amplitude or the phase. So to understand better where this comes from, we plot here the variance of the covariance matrix elements when we change either the coherent coupling or the two-mode squeezing. And what you see is that all these elements are much more sensitive to the fact that you are changing two-mode squeezing than coherent conversion. So I think this is nice because it's another little proof that the advantage really comes from a quantum property in the system and not just encoding in the angle. Okay, so a final thing that I want to show you is that well, training doesn't only concentrate information on a smaller number of degrees of freedom, it also makes the network deeper and more expressive. So this has allowed us to do some a bit harder tasks. So we could do digits, so the compacted 8x8 pixels version of MNIST with 6 coupled modes and with this trick of data re-uploading, where we send input data in 4 different batches that are sent in times that are much shorter than the coherence time of the system. And we can reach 100% accuracy in about, I don't know, 200 and something epochs with just 12 measure probabilities, whereas if we use that same hardware for reservoir computing, we get stuck at 60-something%. Okay, I'm almost done. Just to summarize, so we have seen that training reduces the number of necessary measurements, even including the training. It also allows to do more complex tasks. I mean, this is not such a surprise, right? But we can only efficiently simulate and train linear quantum systems. So we do need other methods, and this is something that we're working on with driven distributive equilibrium propagation and perturbation-based methods. And thank you. You have already seen the group yesterday. It's the same one still.
Thank you so much. Questions?
Hi, thanks for this very interesting talk. I have a small question. The that you use, you mentioned it acts as an ancilla, basically. Does it matter whether it starts at 0 or 1?
Yes, it does. Because for the question that you're asking, you apply a pi pulse. So if it started in 1, then after pi pulse, it's going to be 0.
Right.
And you're measuring, yeah.
So you need to make sure it always starts at 0.
Yes, you do. But you just wait sufficiently long time and it goes to 0.
The errors that you were mentioning, the decoherence errors, are these because of the qubits decoherence times or?
Which decoherence errors?
You know, maybe I misunderstood, but the source of noise, sorry, that you were fine.
Well, the errors that I was mentioning were due to readout because of the Kerr effect. Do you think of those?
Yeah.
Okay, no, so it's not due to qubit. It's due to the fact that when we apply the pi pulse here, we apply it at the frequency that corresponds to n photons in the cavity. But you see that that frequency is not fixed. It bends to the left. So if here I'm asking the question, it's hitting a bit on the side. So the tone doesn't, the pi pulse is not as efficient as it should be.
Thanks.
Nearest neighbor.
Yeah, we do need a snail.
So there is an interesting dependence of the memory of a reservoir on measurement rate. So depending on how long you measure? Because you're doing.
Are you talking about measurement-induced dephasing?
Hmm?
Are you talking about measurement-induced dephasing?
Oh, no. The memory depends in an interesting way on the measurement rate. So I wonder, like, how long is the typical memory in this task of sending the sine wave? You know, it needs to know a little bit before about the previous.
Yeah. Okay. Yeah.
How far does it know physically?
So I skipped some details, of course. So yeah, as when we perform these projective measurements, so we need to reinitialize the system. So in ideal case, we would maybe send the whole sequence, but we actually just send the one previous point, which is a certain version of a task. We could send more, but for this task, it's enough to remember one. I didn't show the results today, but we have also done a chaotic time series prediction, and then in that case, we send the previous 100 points.
And how long is the memory?
So the memory comes from the quality factor of the resonator. So in our case, it's of the order of 3 microseconds.
So it actually may not, depending on how you weekly measure along the way.
So we perform strong.
Determines the.
No, okay, right. But we perform strong measurements here. So here we project the system, and then we don't do.
Projective.
Yeah, here it's always projective, but it's a different implementation that is interesting in itself to do a weak measurement, and then in that case, you could, but then you have measurement-induced dephasing, so your effective memory is shorter, and it depends on how strong the measurement is.
Thank you for the great talk. It's probably my lack of knowledge about qubits, but you mentioned that, okay, this kind of dispersion-looking curves, they bend to the left here, and that affects the measurement, and you said that you cannot change the qubit drive frequency to read them out properly. Why is that?
You can, but if you do it, you're actually giving more information to the system. I mean, you're you're telling it. So how would you, okay, let's make a thought experiment. What would I do? So let's say I am sending the input point, which I know is encoded at this amplitude, and then I correct the frequency of the pi pulse such that it hits well at that amplitude. But then I have already I have given additional information to the network. So we have done this actually in the beginning, to be completely honest with you, and then we realized that it's working too easily. So we realized that we are making the task simpler by doing that. So it's kind of unfair. It would be an unfair comparison.
Fair play, yes.
All right. So let's move on to the next speaker and thank Danijela. So the last speaker this morning is Logan Wright from Yale. He's going to speak on the possibility of a virtuous cycle between photonics and computation.